All right, so we're going to look at the dipole moment and bond polarity and then graduate to molecular polarity. So I have A and B here bonded together. I have a dipole moment drawn. Watch what happens to that dipole moment if we make the electronegativity the same. It disappears because then you have a non-polar molecule. So let's turn some things on over here. Let's turn on electrostatic potential. And let's turn on bond character and partial charges. All right, so right now this is a non-polar molecule, and this electrostatic potential is going to show us blue as positive and red as negative. So if we modify this now and reduce the electronegativity of A, we see that dipole moment grow. We see these partial charges show up to say this side of the bond tends to be positive, this side of the bond tends to be negative. If we look at our dipole moment, we'll see that the tail of the arrow looks like a plus sign, and that's going to indicate the positive side of the bond, and the arrow is going to point to where the electrons tend to migrate. And electrons are negative, and where they migrate, because electronegativity of B is higher, that's going to make this side of the bond negative. All right, so now we're going to move on to 3 atoms. All right, so for 3 atoms, let's turn on our bond dipoles. Now, this yellow dipole is the sum of these two. So when you add vectors, the angle of the vector makes a difference. So if we combine these vectors, we end up with an overall polar molecule where the B tends to be negative and the A side tends to be positive. So let's turn on the partial charges, and you'll see that reflected there. And I thought I could put electron density here, but apparently I cannot. So this idea of a combined overall dipole moment is interesting, and that is contributed not only by the bond polarity, but also by the overall shape. Now that we know something about shapes, this is a bent molecule, and that leads to the molecule being polar. So when we look at the overall molecule, you have to consider the dipole moments of the bonds, but you also have to consider shape. So let's take a look at some real molecules. And I want to turn on electrostatic potential like we did before. Let's turn on the partial charges and the molecular dipole. All right. So this is the hydrogen fluoride molecule. So it's hydrogen bonded to fluorine. We see the electronegativities. Actually, I didn't turn that on. Let's put the atom electronegativities on. There they are. Hydrogen is 2.1. Chlorine is 4. So it is a very, very, very polar bond. Let's look at our diatomic molecules. Nitrogen bonded to nitrogen. We have no shading of red and blue whatsoever. We have no dipole moment drawn. This is a non-polar molecule. Same thing with O2. Same thing with F2. Even though F is the highest electronegativity possible, when it's bonded to itself, it still results in a non-polar molecule. Water. Look at how very red water is and how very blue. Now we're going to look at some other molecules that are polar, but water is extremely polar. Look at the size of this dipole moment here. Let's compare that to the polarity of ammonia. So ammonia is pretty polar. It's that trigonal pyramidal shape. It's not quite as polar as water in terms of the shading and in terms of the size of the dipole moment, but it is pretty polar. What about formaldehyde? It is pretty polar. So in this case, the bond polarities in conjunction with the shape make it polar. All right, so let's go down here to CF4. Carbon is 2.5, fluorine is 4. That's a pretty significant difference. Those bonds, let's turn on bond dipoles for just a minute. It's so gray, it's hard to see. Those